Okay, Chapter 5, Section 2, the definite integral. Okay, in the previous section, we ran into a limit of this form. The limit as n goes to infinity of the Riemann sum as I goes from 1 to n of f of x sub I star times delta x, which can be expanded into the limit as n goes to infinity of the sum of all these products. So f of x sub 1 star delta x plus f of x sub 2 star delta x and dot, 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 all the way out to n. So let's take a minute and refresh our memories of what this means and where it comes from. Okay, so in the previous section, we explored the area problem. So if we are given some function f of x, in this case, we were initially just interested in cases where f of x was positive above the x-axis for some subdomain from A to B. And we're interested in finding the area in blue. That's what we did in the previous section. Okay, so what we do is we start off by taking our segment from A to B, and we find these delta x's. Remember, delta x is equal to b minus a divided by n. Okay, now once we have the delta x value, then we're going to come into here and break this up. So we're going to start off with, well, let's start off with x sub 1 there, x sub 2 there, and dot, 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 dot. Therefore, of course, the first one then is x sub naught. X sub naught is also equal to a. And we go all the way out until the end, and we end up with some x sub n value. Okay, somewhere in the middle, we're going to have some ith value, so let's just label it there, say some x sub I value. Okay, so we break it all up, and we know that each one of these widths is going to have the delta x value. That's how thick it's going to be. So we partition off the domain from A to B, and so we break up the segment from A to B. From A to B is kind of broken up into x naught, which is also a, up to x sub 1, and then x sub 1 up to x sub 2, and so on and so forth. Somewhere in the middle, we're going to have the x sub ith one. So the one that came right before it would be the x sub I minus 1 value, dot, 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 dot. And then somewhere at the end here, we'll have the last one, which ends at x sub n. So the one that came right before it would be x sub n minus 1. Okay, so we partition it all up like that. Each width is delta x. And then what we're going to do is do representative rectangles. Right, so here's a nicer picture for that. Okay, so here is a nicer graphic of this guy, just kind of blown up a little bit. And so what we're going to do is we're going to come up with all these rectangles. We're going to have initially n rectangles, and we want to find the sum of the area of those n rectangles. So we've partitioned off our segment from A to B. So remember, this A right here is x sub 0. And then x1, x2, x3, dot, 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 all the way out to the last one. And the last one is x sub n. The width of all of these rectangles, all of them have the same width of delta x. That one's delta x. And that one is delta x. The ith one, somewhere in the middle, we have I. That one is also a width of delta x. All of them have that same width, which is determined by this formula right here. Okay, so now if we focus on the ith one, in the previous section, we first thought about different rules to determine how tall those rectangles are going to be. We can have a right-hand rule where we focus on the base of each rectangle. So for example, say for this base down here, for the very first rectangle, how do we determine the height of that rectangle? One idea was to use the right-hand rule. That would mean to use the point farthest to the right in the base of the rectangle. That would make the height of that rectangle right around there. Or we can use the left-hand rule, which means that we use the point that's to the farthest to the left of that segment, which would mean it would make the rectangle about this tall. Going out to the ith one, if we use the left-hand rule, right? So in the ith one, the ith rectangle, here it is, from x sub I minus 1 all the way out to x sub I. If we use the left-hand rule, then we would use this point as the height of the rectangle. And if we use the right-hand rule, so here's the left-hand rule, and the right-hand rule would be to use x sub I, which would mean it would be about that tall. Okay, so that was one process that we can use. But then later we introduced this idea where it doesn't have to be the left end or the right end. It could just be some random value in the middle, and that's where these little star ones come in. So x, the sequence of x stars, represent randomly selected values that are within the base of each rectangle. So x sub 1 star is any random number in this base. So this is sort of selected at random right now. So just something chosen for you to visually see. But it could be anything. So notice in this first rectangle, x sub 1 star is far to the left. In this rectangle, x sub 3 star is kind of far to the right within its own base. If you think about the base of that third rectangle, x sub 3 star is to the right of the middle, so it's not quite there, and so on and so forth. So we kind of randomly pick them. The x sub I star looks like it's kind of right in the middle, but that's just sort of by accident. It could be anything. Okay, so we'd say that the list of star values, x sub 1 star, x sub 2 star, x sub 3 star, dot, 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 all the way out to x sub n star, are sample points, are a collection of sample points. Okay, so now that's where this comes from. The product of these two, if we think about these two right here, this is the area of the first rectangle. That's this rectangle right over here, this first one. This first rectangle is that one. It's got a base of delta x and a height determined by f of x sub 1 star. One randomly selected value within its base gets you up a certain height. So at this point for this rectangle, this turns out to be the height we use because it matches the x sub 1 star input value evaluated, f evaluated at x sub 1 star. Good. And then the second rectangle, its height is determined by evaluating our function at x sub 2 star. That determines that height, which means that we get a height times a base. Therefore, this represents the height of the second rectangle. So that would be this one. And so on and so forth, and so on and so forth. Somewhere in there you have the ith one if you wanted to write it down. And then there's the very last one, which is going to be a rectangle that still has a width of delta x and a height determined by evaluating our function at x sub n star. Good. All of that can be represented by this Riemann sum notation. And then once we have an approximation of the area by finding a sum of n rectangles, and we've established a nice pretty formula for it, then we let the n go out to infinity. We have a sum of n rectangles where n goes out to infinity. And if that limit exists, then we no longer have an approximation. That is going to be the exact area. Once again, to visually demonstrate this process, let's say I have the equation sine x plus 1.5. So here's sine x, and it's been transformed up vertically by 1.5 units. Okay, so let's say that I wanted to approximate the area. Let's go from 3 to 9. Let's go from 3 units to 9 units. From 3 to 9. So we would be interested in this area right there in gray. That would be the exact area in gray. But we're going to approximate it. So let's approximate it by starting with 2, and let's use the midpoint rule. So there's 2 rectangles. And in this case, I'm using the middle of each base. For each rectangle, I look at the base, and I'm going to go right in the middle. and that's what establishes the height. Right? That's what the midpoint rule is. Okay, so we can see that if I add up these two rectangles, that would make an approximation of that area, but it's not a great approximation. But then if we go to 3 rectangles, that looks a little bit better. And then 4 rectangles looks a little nicer, and so on and so forth. So the more rectangles I do, the better the approximation. So right here at 12 rectangles, that's a pretty nice approximation of the area between 3 and 9. Of course, we can still see that it's not very precise. There's a lot of gaps here that are white, showing that we're not counting those little gaps. And there's also a lot of little spaces, like this little corner here, that are being included into our sum that shouldn't be included, right? So it's not a very, it's not an exact answer, but we see that it's getting pretty good. And the more rectangles we include, the better and better that approximation is going to get. So we create a process where we find a formula for the sum of n of these, and then if we let the limit go out to infinity, as the number of rectangles goes out to infinity, we see that at infinity, if we can find that limit, then the sum of all these rectangles is equal to exactly the answer we're interested in. It's exactly equal to that gray area. Okay, so that's where this formula comes from. So far, though, we have been very careful to only let f of x be a function that is positive within the domain of a to b. But that doesn't always have to be the case. We will see in this chapter that f of x is allowed to go down into the negatives, and we'll see how we can interpret that or how we deal with that. Okay, with having said that though, let's introduce the definite integral. Okay, so definition of the definite integral. If function f is a function defined for x between a and b inclusive, we divide the interval from a to b inclusive into n subintervals of equal width with the formula delta x equals to b minus a over n. We let x sub naught equal to a, x sub 1, x sub 2, all the way out to x sub n equal to b be the endpoints of these intervals, right? And then we let x sub 1 star, x sub 2 star, all the way out to x sub n star be sample points in these subintervals, so that x sub I star lies in the ith subinterval, x sub I minus 1 to x sub I. Okay, that's up to now exactly what we just looked at. Nothing different at all. All of this, everything I've just read here, leads up to us being able to set up our approximation for the sum of n rectangles, and then applying a limit so that we can find the area that's trapped between the curvature, the x-axis, and the vertical lines x equals to a and x equals to b. Right? So this is exactly what we've been working with. But now, all we want to do is define this exact same thing with this new notation. Okay, so this integral sign is exactly equal to this. Good, so provided that the limit exists and gives the same value, then the definite integral from f, then the definite integral of f from a to b is defined to be exactly this, provided that this limit exists and gives the same value for all possible choices of sample points. Okay. If it does exist, we say that f is integrable on the set from a to b. Okay, so first of all, let me note that I know that some of you guys have already worked with calculus before. You're familiar with this sign, and you are probably well aware of some of the great shortcuts that are coming our way for finding out for integrating things. We are not using those yet, right? We're just introducing it, and so you kind of have to follow along and do it the way the textbook is teaching us to do it at this point. And then as we develop new techniques, new ideas, we'll incorporate them. But for now, if you're asked to evaluate this, You're not allowed to use those great shortcuts. This is exactly this, right? This is that. So we can go back and forth between the two. But if you want to calculate things, then this is how you do it. You gotta take your integral, convert it into a limit as n goes to infinity of a Riemann sum, and then hopefully try and figure it out from there. Or you can approximate it. Maybe it might say, given this integral, approximate it. So you convert it to this, and then maybe do n equals to 6 or 10 or something manageable, and do a nice approximation. If they want the exact answer, then you're going to have to figure out a nice pattern using n of them, and then take the limit. Hopefully the limit exists, and we saw an example like that already in the previous section. We'll probably see one again in this section. Okay, note number 1, the symbol, this symbol here, the integral sign, was introduced by Leibniz, mathematician Leibniz, and is called the integral sign. It is an elongated S and was chosen because an integral sign is a limit of sums. In the notation, the integral from a to b of f of x dx, the f of x is called the integrand, right? So the function inside here is called the integrand. And then a and b are called the limits of integration, right? A is the lower limit and b is the upper limit. So the lower limit, the upper limit, the integrand, and then and for now the dx has no meaning itself. We'll revisit that in the future. Remember that this whole thing, you should think of it as one big sign. It needs to be together. You cannot have a situation where you don't have the dx there. It has to be there. And likewise, you can't, you have to put it in this order in the way it is when you do it. So, likewise, you can't have this. We can have the square root of 4. That makes sense. We can't have 4 square root, right? That doesn't make any sense. So we have to have, you can't have the integral AB, from a to b and put our function out here. That doesn't make any sense, right? Just like that. So it's got to be the integral sign from a to b, from the lower limit to the upper limit of f of x, and then we have to have the dx there. Again, it just doesn't make sense not to have it. So we have to have it. Think of it as one united symbol, and this represents that limit as n goes to infinity of the Riemann sum. So the dx simply indicates that the independent variable is x. So for now, all that's really important is to make sure that this function in here, the integrand, is a function defined with a variable that matches whatever this is. It doesn't have to be x, of course. It could be any letter, but they have to match in order for the integral to make sense. Okay, note 2, the definite integral from a to b of f of x dx is a number. It does not depend on x. In fact, we can use any letter in place of x without changing the value of the integral. Okay, so we call these dummy variables here, f of x, f of t, f of r, right? It doesn't matter whether you use an x, a t, or an r. They can both be expressing the same thing. Remember that I know that in algebra, x usually represents an independent variable, an unknown value to be determined, some value you can choose to affect the output, right? That's what we think of when we think of the letter x, but that's not what it is in this context. Remember that these input values to this function, let's go back to the definition. These input values here, sometimes we use the little star notation and sometimes not, but either way, these values are the ones that refer to this one, and they represent a sample point, right? A sample point chosen from our domain that is used to determine the height of the rectangle, right? It's not up to you to choose it. It's not we're not going to solve for it. It's not like an algebra problem where we solve for x sub I star. That's not what it is. It's a sample point. And in practice, when we're doing 6 rectangles, maybe 5 rectangles, we'll actually physically figure it out and get a calculation for the input values x sub I star. But beyond this section, as we increase the number of rectangles, it becomes impractical to actually figure out these sample points. We just know they're there. And as we'll see in this section, as delta x becomes infinitely small, then we'll be able to take some infinitely small, we'll be able to make some assumptions that makes these calculations much easier. Okay, so for the time being, note 2, it doesn't, this is not the traditional kind of x. Just keep that in mind. We're not solving for x. This is not an algebra problem where you get to choose your own x. This whole thing is representative of that limit of a Riemann sum. And these x's represent the heights of each individual rectangle. Dx represents the width of each individual rectangle. And we're going to find n of them, and then let n go out to infinity. That's what this whole thing represents. Okay. All right. So and then make sure that these things match. If there's the letter t in here, then this is dt. If there's the letter r in here, then this is dr. Okay. Note number 3: the sum as I goes from 1 to n of f of x sub I star delta x that occurs in definition 2 is called the Riemann sum, after German mathematician Bernhard Riemann, all the way back in 1826 to 1866. So definition 2 says that the definite integral of an integrable function can be approximated to within any desired degree of accuracy by a Riemann sum. We know that if f happens to be positive, then the Riemann sum can be interpreted as the sum of the areas of approximating rectangles. Right, so that's what this is right here. We've been working with this a lot now, so hopefully we feel nice and comfortable with this. So if f of x happens to be positive, then we can interpret this as area underneath the curvature. So when we say the language area underneath the curve, we automatically mean the area trapped below the f of x function, above the x-axis, to the right of the vertical line x equals to a, and to the left of the vertical line x equals to b. Right? We can interpret it as area. We see that the definite integral, the integral from a to b of f of x dx, can be interpreted as the area under the curve y equals to f of x from a to b. So if f of x is positive, then the integral from a to b of f of x is the area under the curve y equals to f of x from a to b. And so when we say we're under the curve, we automatically mean under the curve but above the x-axis. If f takes on both positive and negative values, then the Riemann sum is the sum of the areas of the rectangles that lie above the x-axis and the negatives of the areas of the rectangles that lie below the x-axis. Okay, so remember, each rectangle is a base times a height. Base times a height. So the base is always positive. That's never going to change. But now if the height takes on a positive value, then the area is going to be a positive number. If the height, the value of the function evaluated at a point, turns out to be negative, then that area is going to turn out to be a negative number. Okay, so all the places where the function is negative, we're going to get negative answers for our rectangles. And if we add them all up, we'll have a negative number to represent the whole area below the x-axis, and all the ones that have positive outputs for f of x will result in positive areas depicted here in blue. So the positive ones are in blue, and the negative ones are in this gold color. So f of x, the sum of f of x sub I star delta x, so the sum of all those rectangles, is an approximation to the net area. So the net area is going to be to add up all the positives minus the negatives. So a definite integral can be interpreted as a net area, that is, the difference of areas. So the integral from a to b of f of x dx is equal to a sub 1 minus a sub 2, where a sub 1 is the area of the regions above the x-axis and below the graph f, and a sub 2 is the area of the regions below the x-axis but above the graph f of x, so as we depict here. So this is saying that a sub 1 is all the positives. So the sum of this plus this, both of those represent a sub 1. And then the sum of just this part here, this one is a sub 2. So we add up all the a sub 1s and subtract the a sub 2. That would be the net area. And that's what this integral sign will depict. So obviously, if the areas above the x-axis equal the areas below the x-axis, the answer is going to be 0. So just from the picture, by looking at this could quite possibly be an answer of 0, right? That's a possible result. Or the answer could also be negative. Maybe the gold area here is actually bigger than the sum of the two blue ones, and so my answer could be negative. Right? You just have to be careful about the details of how you do it and how you calculate it, but a negative answer is perfectly reasonable. Okay, note 4. Although we have defined the integral from a to b of f of x dx by dividing the segment from a to b into subintervals of equal width, there are situations in which it is advantageous to work with subintervals of unequal width. If the subinterval widths are delta x sub 1, delta x sub 2, all the way out to x, delta x sub n, we have to ensure that all of these widths approach 0 in the limiting process. This happens if the largest width, the max delta x sub I, approaches 0. So in this case, the definition of the definite integral becomes this. So the only thing that's different from before is that before we had n goes to infinity, and that n was enough to guarantee that we'd have a growing number of rectangles, from n rectangles out to infinite rectangles, and that we were adding up all those areas. And that's because before, in the previous definition, we were counting on delta x to be a constant, b minus a over n. Right? So as previously thought of, the delta x was b minus a over n. So it represented a constant width. So all the widths of all the rectangles were the same. There are some very unique situations where we might not want that. Some rectangles are skinnier than others. We probably will not run into that in this class. That's more of an advanced move. But it's nice to be aware that it can happen, and maybe in a future class of yours, if you take more math classes, you'll run into this. But for now, this really shouldn't be a big issue for us, just making you aware that it happens. Note 5. So we've defined the definite integral for an integrable function, but not all functions are integrable. The following theorem shows that the most commonly occurring functions are in fact integrable. The theorem is proved in more advanced courses. We don't have to worry about that here, but it gives us the freedom to be able to work with a good variety of functions. So theorem 3 says that if f is continuous on the set from a to b, or if f has only a finite number of jump discontinuities, then f is integrable on a to b. That is, the definite integral from a to b of f of x dx exists. Okay, so the bar has been set pretty low. All we have to establish is that either the function we're working with is either continuous on a to b, it doesn't even have to be differentiable. If f is just continuous, it's good enough. We don't have to guarantee that it is differentiable, just continuous. And even if it's not actually continuous, but there are a finite number, a countable number of jump discontinuities. So even if it breaks off a little bit, doesn't go off to infinity, but it could just break off a little bit and have discontinuities, then f is still integrable on the set from a to b. Okay, so let me show you what we mean by these finite number of jump discontinuities. So for example, if we have f of x like this, y like that, and we have some function. Okay, so here is continuous. Here is a continuous function from a to b. Okay, so obviously that area is going to exist. On the other hand, if f of x is not continuous, but maybe it does this. Maybe it kind of goes up to there and then has an open circle and then has a little closed circle there and then it does that. Then there's only one jump discontinuity there. As you can imagine, we can still easily think about the area underneath the curvature. It's going to go from there out to there. And then here we can kind of imagine this little dashed line there. So in this situation, the area underneath the curvature would kind of look like this. So it's still manageable and defined, and we can visualize it. And even if there's 2 of these, or 3 of these, or 7 of these, we can still imagine the area underneath the curvature is going to exist. It only becomes unmanageable when we have an infinite number of jump discontinuities, or if we have a situation where the function jumps up to infinity. Or if the function is doing this kind of thing, goes off to infinity, and then maybe comes this way like this, right? If this is our function, then we have a problem, right? Because how do we define the area from here to here if there's a vertical asymptote in the middle, right? So that's a little bit more problematic. It's not an automatic no. We'll see how we deal with these things later on. But for now, we're just sticking to this theorem that exclusively says that if it's continuous or it has a finite number of jump discontinuities, we're okay. Now this thing, well, that's complicated. We'll deal with that later. This is not addressing that situation. Okay, so theorem 3, if f is continuous on a to b, or if f is only a finite number of jump discontinuities, then f is integrable on a to b. That is, the definite integral from a to b of f of x dx exists. If f is integrable on from a to b, then the limit in definition 2 exists and gives the same value no matter how we choose the sample points x sub I star. Okay, so that's why it doesn't really matter. We don't really spend much time trying to calculate the values of x sub I star, only in cases where we're only going to have 5 rectangles or so. Beyond that, we don't really bother trying to figure those specific values out. It turns out that it could be any sample, any selection of sample points, and you get the same answer. To simplify the calculations of the integral, we often take the sample points to be the right endpoints. So if you get the same answer no matter what sample points you choose, why not just make life easier and just happen to choose the right endpoint, thereby making the sample points be exactly equal to the x sub I values. And then the definition of our integral simplifies just a little bit more in the following way. So theorem 4 says that f is integral on a to b, then it's equal to this. The integral from a to b of f of x dx becomes the limit as n goes to infinity of the Riemann sum as I goes from 1 to n of f of x sub I delta x. Right, so the only thing that's different is that before we used to have an x sub I star here, which represented a sample point. But now we're saying let's use the right n rule. And now we keep the same definition for delta x. Delta x is b minus a over n. And now we have a more precise definition for the input values of our function, which represent the heights of our rectangles. Right, we worked with this before. Okay, so here's an example. Express this limit, the limit as n goes to infinity, as I goes from 1 to n, of x sub I cubed plus x sub I sine of x sub I delta x. So just express it as an integral is the question. It doesn't say to solve it. So to express it as an integral, very, very easy. So it's going to be some sort of integral, of course. Now the limits of integration, they're not found here. They're kind of buried inside here, or they're given to you, right? So remember that delta x is b minus a over n. So either this will kind of be given to you, or as in this example, it's given here. This is the a, this is the b, right? So even though they didn't give it to you, the delta x is really equal to pi minus 0 divided by n, or pi over n. So keep in mind that this question could have been even more confusing if instead of giving you this, they said this, and then there was like a pi n here. And you're like, ooh, extra weird. But luckily they didn't give us that. So there it is, delta x. Okay, so the limits of integration, they start off from a to b. So this is from a runs from 0, b goes up to pi. And then this guy right here, the only thing that changes is now it's a function of x. So we're just going to write it as x cubed plus x sine x. We don't have to worry about the subscript I anymore, because when it's over here, I, it represents to this counter, right? Here we're counting the sum of rectangles, where this is the base of each rectangle, and this function evaluated at each one of these input values represents the height of each rectangle. So we had these little I subscripts that were connected to this Riemann sum. But with the integral notation, we don't need that. So there's no i's there. So here's our function. And now remember the whole thing, the whole function, and then we have a dx there. And that's it. That's our notation for it. It didn't ask us to find the answer. It just said write it as an integral. And that's our integral. Okay, evaluating integrals. Okay, when we use a limit to evaluate a definite integral, we need to know how to work with sums. The following three equations give formulas for sums of powers of positive integers. So hopefully these look familiar from your pre-calculus days. So these formulas help us figure out how to add some patterns that establish. So for example, let's work with this one. So what this is saying is that, for instance, if I wanted to add 1 squared plus 2 squared plus 3 squared, let's say 4 plus 4 squared. If I wanted to add these up, that would be this one where n equals to 4. Right? This is the same thing as the Riemann sum as I goes from 1 to 4 of I squared. That's what this means. And I mean, I could physically do it, no problem. That would be 1, 4, 9, and 16. 1 plus 4 plus 9 plus 16. That gives me 25, 30. Right? All of this is 30. Not bad. But this formula tells me that, well, instead of actually calculating them like this, you can plug them into this formula. And so the formula here, remember, n equals to 4. So we have blank, and then we have blank plus 1 times 2 times blank plus 1 divided by 6. And then we have a 4 there, a 4 there, and a 4 there. So just to confirm, we get the same answer. Let's see, we get that this is 4 times 5 times, and that would be 8 times 8 plus 1 makes it 9. So we have 9 times 5 is 45, times 4 makes it 180. 180. And 180 divided by 6 gives you exactly this number, 30. Okay, so you're wondering, why in the world would I do this when I can easily do that? Well, that's just because there is only 4 of them. If I wanted to add a much larger one, like say 1 squared plus 2 squared plus 3 squared, keep going in that pattern, and don't stop until you get to 88 squared plus 89 squared plus 90 squared. Doing this process, each one of these squared all the way up to 90, and then adding them up would be incredibly hard. And this is much easier. I can just say, oh, okay, well, that whole thing is just going to be equal to 90 times 91, so 90 plus 1, times, and then 2 times 90 plus 1, two times 90 plus 1, and then all of that divided by 6. Okay, so that would be 90 times 91 times 181. So, okay, kind of a big multiplication. And then all that gets divided by 6. But clearly much easier than doing it this way. And also, it gives us a formula in n. And as we've seen, that's important because the next step is going to be to let n go out to infinity and see if we can figure out a pattern that is established as n goes out to infinity. Okay, so these are three very popular ones. If we just add up 1 plus 2 plus 3 plus 4 all the way out to n. If we add up 1 squared plus 2 squared plus 3 squared plus 4 squared all the way out to n. Or cubed, 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed, and so on and so forth all the way out to n. We get some nice closed formulas for them. Okay, so in this section, when we're asked to find an integral, we're going to have to rely on these formulas quite a bit. Remember, we don't get to use any of the integral shortcuts that some of you might already know from a previous calculus course or something. Here we have to do it this way for now. We also need some nice properties of Riemann's, so these might come in handy as well. We know that if we're summing up from I equals from 1 to n of just a constant c, then that's equal to n times c, right? So for example, if we were just adding up from I goes from 1 to 9 of the number 3, well, this is just saying that it's 3 plus 3 plus 3 plus 3, 1, 2, 3, 4, dot, 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 all the way up to 3, 9 times. Nine times. So this just becomes 9 times 3, right? And that's what this is saying. There's going to be c being added up n number of times. That gives you n times c. Okay, we also know that if we have c, which is some constant, times some actual function of I, so notice that the c does not depend on I, it's just some constant. Like here, the 3 does not depend on I, it's always 3. So we can pull out the constant out in front and multiply it times the sum we get. We also hopefully remember that if we have an addition or a subtraction inside the argument of our sum here, then we can separate it into the sum of two Riemann sums. So the Riemann of a sum is the sum of two Riemanns. Good, so we can separate it that way. That would also help us figure out our calculations. Okay, so for part A, we're going to start off by taking our segment from A goes from 0 to 3. So here's our line segment. Here's A equal to 0, and then B equal to 3. I'm going to break this up, break up our domain. So we have to think about our delta x value. Our delta x value is equal to 3 minus 0 divided by n. And in this case, n was 6, so it's going to be 3 over 6, which is equal to 0.5, 1/2. Okay, so that means that, let's make our list of x naughts. X naught is going to be 0. X1 is going to be equal to 0 plus a delta x. X2 is going to be equal to 0 plus 2 delta x's. X3 is going to be 0 plus 3 delta x's. And so on and so forth. Okay, so let's find out the actual value. This is going to be x naught equals to 0. X1 equals to 0 plus 0.5 is just going to be 0.5. And x sub 2 is going to be 1. And x sub 3 is going to be 1.5. And x sub 4 is going to be 2. And x sub 5 is going to be 2.5, and finally x sub 6 is going to be equal to 3. Okay, so that's how we're going to break this up. This point right there, x sub naught will be 0, over here we'll have 1, 2, 3, 4, 5. Well, not exactly. They're supposed to be equal looking, but that's okay. X sub 6 equals to that guy, x sub 5, x sub 4, x sub 3, x sub 2, x sub 1. Good. Okay, and then remember that, okay, so all of these have the same width of delta x. All of them are supposed to be the same width, even if it doesn't look like it. And then we're going to create rectangles above. So we're going to have a rectangle right above each one of these. So maybe this goes out to there, and then the next rectangle maybe goes out to there, you know, something like that. And how do we determine the heights? Well, we evaluate the function. We evaluate this function at one of the points within the base of the rectangle. And we can use any rule we want. Oh, no, never mind. They said use right endpoints. Okay, so let's figure it out. So that means that r sub 6, since we're going to use 6 rectangles, represents the first rectangle. Well, that's just going to be f of x sub 1 times delta x plus f of x sub 2 times delta x plus dot, 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 all the way out to the last one. Oh, actually, I better not dot, dot, dot and just actually write them down. So this becomes f of x sub 3 delta x plus f of x sub 4 delta plus f of x sub 5 delta x plus f of x sub 6 delta x. Okay, well, this sum, they all have a delta x in common, so let's factor out a delta x. So f sub 6 equals to delta x, f of x sub 1 plus f of x sub 2 plus f of x sub 3 plus f of x sub 4 plus f of x sub 5 plus f of x sub 6, right? Factoring out, that, you know, noting that they all have a factor of delta x that we can factor out. And delta x, as we determined, was equal to 0.5, so this just becomes r of 6 equals to 0.5 times. Now, for each one of these, what we want to do is evaluate our function at our x values. So this would be f of 0.5 plus f of 1 plus f of 1.5 plus f of 2 plus f of 2.5 plus f of 3. Good. Okay, so now each one of these values is determined by valuing our function at each one of these points. So this point right here, this one, is going to be 0.5 to the power of 3 minus 6 times 0.5. And that gives me, this result is this one. Okay, next, okay, the next one is 1. So the next one is going to be plus, and then it'll be 1 cubed minus 6 times 1. And that takes care of this one. So this one is that one. And so we do that for all 6 of them. So this is, let me put parentheses around it, this one, and then this one, plus, and then the next one is 1.5 to the power of 3 minus 6 times 1.5. That takes care of the next one. I'll put it over here, plus 2 to the power of 3 minus 6 times 2 plus 2.5 to the power of 3 minus 6 times 2.5 plus finally 3 cubed minus 6 times 3. Okay. Let me put them in blue parentheses, maybe that'll make it easier for them to pop out. So this is that first one, and then this is the next one, and then this one, and then this one, and this one, and then that one. Okay, and then the entire thing, all of it, is multiplied by this 0.5. So we have all of that, and all of this is being multiplied by 0.5. 0.5 equals to r sub 6. Okay, well, this would be a great time to use the function feature in your calculator to figure out each one of these things, so you don't have to crunch them all out by hand. So let's use that. Okay, with your calculator, let's hit clear here. Let's go to y equals, let's get rid of, oh, so I already have 6 cubed minus, so type in 6 cubed minus 6, oh, not 6x, not 6x squared. There we go, 6x, there we go. So x cubed minus 6x, and notice that this equal sign is dark, that one is not, so this is not going to bother me. Next, let's go over to table set, second table set. 0 there, 1 there, it doesn't matter what that is, but this I want it to be independent is under ask, and dependent is under auto. Use your arrows, come down, and hit enter if you want to select something else. Okay, and next we're going to go over to table, so second table. And whatever numbers are there already, just delete them, hit delete, delete, delete. Okay, so this is a place where we input an x value and it will automatically cube it and minus 6 times that input, so it automatically calculates the output of this function. So that's very useful here because we can use it to find these answers really quickly. So if we type in 0.5, we get that first one. So this is the height of the first rectangle. It's below the x-axis actually, right? So it's going to be a negative answer. That's okay. We're allowed to have that. The next one is a 1, also negative. The next one is a 1.5, also negative. The next one is a 2, also negative. The next one is a 2.5. Oh, now a positive. And finally, the last rectangle is going to be a 9. So we're going to have 6 rectangles where the base is always 0.5. That's what this little formula was telling us. There are 6 rectangles where the base is always 0.5, and the heights are dependent by these values. The height of the first rectangle is negative 2.75. The height of the next rectangle is negative 5, and so on and so forth until we get all 6 of them. So we multiply them all, add them together, we come up with the net area, the areas of the positives minus the areas of the negatives. So let me copy these down. Okay, so if we copy them all down, we get approximately this. Remember that 1/2 times this number is the area of the first rectangle. 1/2 times negative 0.5 is the area of the second rectangle. 1/2 times negative 5.625 is the area of the third rectangle, and so on and so forth. And if we figure out this calculation, we're going to get approximately r sub 6 equals to 3. R sub 6 is going to be to negative 3.9375, approximately. Okay, so this becomes our best guess for the area in question. And it's just an approximation using 6 rectangles. Of course, if we want a better approximation, all we have to do is do more rectangles. Okay, so here's what your author provided. So with n equals to 6, then we find our delta x value to be equal to 1/2. That helps us figure out all our right endpoints, just like we did. And here is our Riemann sum with 6 right endpoints. Right? We use capital R to identify that we're using the right end rule. which is the sum as I goes from 1 to 6 of f of x sub I delta x. And so we calculate this to be that, we get the same answer. Okay. Notice that f is not a positive function, and so the Riemann sum does not represent the sum of the areas of the rectangles, but it does represent the sum of the areas of the blue rectangles above the x-axis minus the sum of the areas of the gold rectangles below the x-axis. We get a net sum. When you think of areas in, say, geometry, area is always a positive number, right? So here we're identifying the rectangles that are below the x-axis as having a negative number. Okay, now let's take a look at part B. Evaluate the integral from 0 to 3 of x to the third power minus 6x dx, right? So it doesn't say approximate it, find the exact answer. So we know that that must mean that we have to use this formula. The integral from 0 to 3 of x to the third power minus 6x dx is equal to the limit as n goes to infinity of the Riemann sum as I goes from 1 to n of f of x sub I delta x. Okay, so we got to come up with a formula here using n rectangles and then apply the limit as n goes to infinity. So first of all, let's think about our delta x. Our delta x then is equal to b minus a over n, which in this case will be 3 minus 0 divided by n, or just 3 over n. All right, now let's think about our partition points, which will also act as our sample points. If this is the x-axis and we go from 0 all the way out to 3, we're going to break this guy up. Okay, so this one will be x sub 1, x sub 2. We start off by x sub 0. And then we keep going until we get to the last one, which would be x sub n. X sub n is equal to 3. The one that came right before it would then be x sub n minus 1. And then along the way, we have to think of one somewhere in the middle there, which would be the x sub ith value. And then right before that came the x sub ith minus 1 value. Okay, remember, all of these are going to have the same width, delta x, all the way throughout. This one's also delta x. And we learned that we can use any sample points within the base of any rectangle. So why not use the right endpoint, right? So we'll use the right endpoint rule, meaning that for every rectangle I draw, I'm going to have delta x as a base, and then the height of that rectangle will be determined by the right endpoints. So x sub 1 will be used to determine the height of the first rectangle. F of x sub 1 will be the height of the first rectangle. F of x sub 2 will determine the height of the next rectangle, and so on and so forth. So if we think about the ith rectangle, just kind of insert a rectangle right in here, just to have something to visualize. This rectangle will be determined by this point, which we evaluated by the height, which will be f of x sub I, right? Delta x. Okay, good. So now that we have all that, let's figure out the actual values of x sub 1, x sub 2. So we've established, as we established here, that must mean that x sub 0 is equal to 0. X sub 1 is going to be equal to 0 plus 1 copy of delta x. X sub 2 will be equal to 0 plus 2 copies of delta x. Zoom out here. X sub 3 will be equal to 0 plus 3 copies of delta x. Right? I have 0 here because we just happen to have started at 0 every time, because the integral was to be, we're asked to integrate from 0 to 3. Okay, so this x sub 3 is equal to 3 multiples of delta x. There's a delta x, and here's another delta x. There's 1, 2, 3 multiples of delta x plus the starting point, which happens to be 0. So we get that. Now, in every one of these cases, the delta x is 3 over n. So another way of saying this is that x naught is equal to 0, and x1 is equal to just one copy of the delta x, which is just going to be 3n. And x sub 2 is equal to 0 plus 2 copies of the delta x, which is 3 over n. That's going to give me 6 over n. X sub 3 is equal to 3 copies of the delta x, which is equal to 3 over n. That gives me 9 over n. And so that establishes a pattern. I'm not actually going to use these numbers. I need them to help me figure out what the pattern is going to be. And I can see that every time it's 0 plus this index multiple of delta x's. So when I get to the x sub ith one, then this is going to be 0 plus I multiples of the delta x. And so over here, dot, 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 that means that x sub I is going to be equal to I multiples of the delta x, which is 3 over n, which gives me the pattern 3i divided by n. Remember, I does not represent imaginary numbers in this context. It's a subindex to help us figure out the ith rectangle in the ith subinterval, with x sub I representing the value, the sample point used to establish the height of the ith rectangle. Okay, and if we kept going through that pattern, obviously then, dot, 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 if we keep going, eventually we reach the nth one, which would be 0 plus n multiples of delta x, and x sub n over here would be n times 3 over n, and of course the n's cancel to give us exactly what we would expect. The nth value is equal to 3. Okay, but the one I'm really interested in is going to be the ith one, right? Because we want to establish a pattern. And so that's what I'm going to use. 3i over n as the input value in my Riemann sum. So let me come back up here. And now I'm set to continue with this. So I'm going to copy this over here. I'm going to say that the integral from 0 to 3 of x to the third power minus 6x dx is actually equal to the limit as n goes to infinity of the Riemann sum as I goes from 1 to n on the function f of x sub I delta x. And now this is equal to the limit as n goes to infinity of the Riemann sum as I goes from 1 to n of f of, and now I have a better statement than just saying x sub I. Now we just established that the x sub I value is actually 3i over n. So that's what I put right over here. This is 3i over n is the x sub ith value times delta x. And delta x, actually, delta x is also an established value. It's right here. Delta x is equal to 3 over n. I'll zoom out in a little bit and we'll see everything all at once. But the delta x is the 3 over n, and the x sub I is 3i over n. So coming back over here, I'll just cap it right here. X sub I was established to be the 3i over n, and delta x was established to be 3 over n. So I'm just going to replace this guy then by times 3 over n. Now 3 over n has no I index. So the I, when I equals 1, when I equals 2, it affects this. But it doesn't affect that at all, so we know we can bring it out in front, right? Take it out of the Riemann sum. Now it is affected by this limit because this has an n and that has an n. So we can't pull it all the way out in front, but we can pull it outside this Riemann sum. So this would be equal to 3 over n times, and now the Riemann sum as I goes from 1 to n of this function, f of 3i over n. Now, again, recall that here is our function. F of x is equal to x cubed minus 6x. And so this is what we use to guide us to simplify this. I'm going to evaluate this function at 3i over n. So this becomes the limit as n goes to infinity of 3 over n times the Riemann sum as I goes from 1 to n of, and now this says the input cubed minus 6 times the input, so it's got to be 3i divided by n to the power of 3 minus 6 times 3i divided by n. Right? All of that is being influenced by this Riemann sum there. Okay, so now we just simplify this a little bit. We can, cube this and distribute this. So this becomes the limit as n goes to infinity of 3 over n times sum as I goes from 1 to n of 27i cubed over n cubed minus 18i over n. All of this is being affected by that sum. And now we know from our properties of Riemanns that if we have the sum of a difference, it's equal to the difference of the sums. So we can find them separately and then subtract them afterwards. What that means, the limit as n goes to infinity of 3 over n times, and now I'm going to separate this as I goes from 1 to n of 27i third power over n to the third power minus the sum as I goes from 1 to n of 18i over n. So kind of two separate things, and the 3 over n applies to both of them, so we can multiply it like that. So up here this was times all of it, so I introduced those extra brackets. And now we can simplify this a little bit again. Again, if we focus on this, the I is right here, but n to the third power, oh, that's a 3. Let me see if I can make that look a little nicer. N to the third power is not affected by I, and n over here is not affected by I. So we can pull that out of the Riemann and write it this way. This is equal to the limit as n goes to infinity of 3n times, I'm going to pull out the 27 over n to the third power times, and this will be sum as I goes from 1 to n of I cubed minus, and then again pull out the 18 over n, and then this 3 over n applies to that one too, so I'll put a 3 over n times, and then this will be 18 over n, and then sum as I goes from 1 to n of the I. Okay, all right, so these simplify easily. These simplify easily. This is equal to the limit as n goes to infinity of, and then 27 times 3 is equal to 81. 81 divided by n to the fourth power. And then this Riemann sum as I goes from 1 to n of I cubed minus 18 times 3, that's equal to 54 divided by n squared times sum as I goes from 1 to n on I. Okay, so just to be clear, this limit still applies to everything. So I'm just going to put a giant bracket here. This whole thing is being influenced by that limit, just separate it into two pieces. And then again over here, this whole thing is being influenced by that. Good. So it's this fraction times the result of this Riemann sum minus this fraction times the result of this Riemann sum. But all of it is being affected by the limit as n goes to infinity. All right, let me copy that up here. Let me zoom out. Let's put that up here. And so I'm going to say again the integral from 0 to 3 of x cubed minus 6x dx is equal to, and we've established it's equal to this limit, the limit as n goes to infinity of this fraction, 81 over n to the power of 4, and then Riemann sum of I cubes as I goes from 1 to n, minus 54 over n squared, and then Riemann sum of just the i's as I goes from 1 to n of I. Okay, let me zoom into here now. Okay, so again, the limit applies to all of it. And now we have some nice formulas for these. So we just looked at some nice formulas for summing the sum of the first n values, 1 plus 2 plus 3 plus 4, all the way out to n. So put it in a different color here. We found out that 1 plus 2 plus 3 plus 4, the sum of the first n numbers, is this formula, n times n plus 1 over 2. So we can just replace that with this formula. And we also saw that the sum of the first n cubes, 1 cubed plus 2 cubed plus 3 cubed plus all the way out to n cubed, is actually equal to just that. It's n times n plus 1 over 2 squared. Right? Kind of an interesting fact that these two formulas are really close. So I can just replace all of this by this formula. And I can replace all of this by this formula. Okay, so let's do that. So now this integral, I'm running out of space here, so I'm just going to leave it there. That integral is equal to the limit as n goes to infinity of this 81 over n to the 4th power times this number, or this formula, n times n plus 1 divided by 2 squared minus 54 over n squared times this formula, which is just n times n plus 1 divided by 2. Right? Again, all of this is being influenced by that limit. Okay, and so now we can simplify things just a little bit. This is the limit as n goes to infinity. And this is going to become 81 times n to the 2nd power, n plus 1 to the 2nd power. You know, I'm gonna space it out like this for now. This is the n plus 1 squared, so there's 2 copies of it. I'll leave the n squared there. And all of that gets divided by 4, so I'm going to put the 4 out here, and then divided by, and then there's an n to the power of 4, so I'm going to put n to the power of 2 here, and then an n and an n there. So here are my n to the 4th powers there, 2 to the 2nd powers there. Okay, and then I'll put the 54 out here, 54 over 2, and then I have an n plus 1, and then in the denominator I read it as an n and an n. So n squared becomes these two, and then I have an n and another n. Okay, and then all of it is again still being influenced by that limit as n goes to infinity. Bunch of stuff will reduce now. This one will cancel with that one. This one will cancel with that one. And I'll just keep going from there. And now these guys I can divide. So this becomes the limit as n goes to infinity of 81 divided by 4 times, and then if I divide these, I get a 1 plus 1 over n, and then another 1 plus 1 over n from here, minus 54 divided by 2 times another 1 plus 1 over n. Right. All of that gets influenced by that limit as n goes to infinity. Good. So just to be clear, this term, n plus 1 over n, turns into this. N over n is 1 plus 1 over n. Likewise, this term and this one turn out to be this one. And finally, n plus 1 over 1 gives me that one. Okay, the limit as n goes to infinity of 1 over n is always going to be equal to 0. Right? So let's simplify all this. As I apply my limit, This goes to 0, this goes to 0, and this goes to 0. So my whole limit turns out to just be the following. The limit as, well, I've already applied the limit, so I shouldn't write the limit anymore, but that whole thing turns out to be 81 divided by 4 times 1 plus 0, so just times 1 times another 1, minus 54 divided by 2 times 1. Okay, so it's really just going to be 81 divided by 4 minus 54 divided by 2. So let's multiply this by a 2 over 2 to get me to 108 divided by 4. So it's 81 divided by 4. It's 108 divided by 4, which gets me to my result. This is going to be equal to negative 27 divided by 4. Okay, so let me zoom back out and state my answer then. So then I'll just put it right over here, the integral from 0 to 3 on the function x cubed minus 6x dx, after all that work, turns out to be negative 27 divided by 4. Right, and that's my final answer. Let's see if I can zoom out here and get enough. Okay, so that was a long, ugly problem. Again, let me remind you that I know that there are easier ways to solve this, and I know lots of you are very much aware of the shortcuts and awesome, fast ways of finding the answer. But in this section, we don't know those yet. We're going to develop them soon. Coming up, we'll start developing them. For now, if you're asked to find the value of integral by using the limit definition, this is what you got to do. Okay, so you got to refer back to this definition of a limit, convert our integral into this. So you have to come up with a Riemann sum that can define n number of rectangles, the sum of n rectangles, and then use our properties of Riemann sums and some of these really awesome shortcut values to be able to restate our sum in an equation involving n, such that when you take the limit as n goes to infinity, hopefully you're able to get an actual value. Obviously, there's a lot of functions for which this would be incredibly difficult, almost maybe even impossible. So not to worry, your author has very carefully cultivated questions in this section that can be solved like this. And for the harder ones, we will build a whole family of properties and tricks and rules and shortcuts that will help us do those. This is just like when we did derivatives. We first learned the limit definition of derivatives, and we did it for a few sections, a few problems, using that limit definition. Even for simple equations, it was a real pain. But then we developed and we established rules and properties and shortcuts and patterns, and then we were able to really take it to town and do really complicated derivatives. Same process here. We're learning first the limit definition involving a definite integral, and then later when we develop some nice shortcuts, some nice rules, we'll be able to develop nice ways of finding these integrals. This integral will then turn out to be a super, super easy one to do, so you'll really focus your attention on the much more complicated ones. Okay. Here's our nice graphic to visually represent what we just did. The integral from 0 to 3 of our function, x cubed minus 6x. Remember, the function is going to be negative for a little while and then positive. So for a portion of it, we're going to get sort of negative values when we find the integral. And then for a portion of it, we get positives. The integral from 0 to 3 is going to be that net result. And so after all that work, we saw that that answer was negative 27 over 4. And negative 27 over 4 is equal to exactly this. we got that it was negative 27 divided by 4, which is equal to that, negative 6.75. So here's an illustration of finding that integral using r sub n, where n equals to 40. So if we add up 40 rectangles, some of them are going to have negative answers because they're below the x-axis. Some of those rectangles are going to have a positive answer because they're above the x-axis. And so if we add up all the positive ones minus all the ones that are below the x-axis, we get the net area. And so we get that with 40, we get this decimal, right? Remember the real answer is negative 27 divided by 4, which is equal to negative 6.275. So the point here is that when we use 40 rectangles, we don't get the exact answer, but we get a pretty good approximation. And from this table here, we see that with 40 rectangles, we get negative 6.4, approximately negative 6.4. And then with 100 rectangles, we get a little bit closer approximation, negative 6.6. With 500 rectangles, even better. With 1,000 rectangles, even better. With 5,000 rectangles, almost exactly the right value, almost, right? So it just depends on how much accuracy you want to have when you want to do it with some fixed number of rectangles. So even in cases where the limit does not exist, if for some reason we can't apply the limit as n goes to infinity, in some situations, it might be good enough to just get a pretty good approximation out to 1 decimal place or 2 or 3 or 4, and just let n go out to a very large number. Of course, we have the benefit of calculators and computers to help us do these very large cases. So in some real-world applications, that might be good enough. But all we want to establish here is the pattern that as n gets larger and larger and larger, the sum of n rectangles gets closer and closer and closer to the real answer. Using this free online applet, we can also demonstrate the exact same thing. You can type in your equation here, x to the third power minus 6x, and x ranges from 0 to 3 in our case. Let's begin by really simple, let's just say 2 rectangles, using the right point rule, and plot that. And that's what it looks like. So here's my function. Part of it is below the x-axis, part of it is above. And we can see that the actual area, they tell us it's negative 6.75, as we very painfully calculated. This is the actual answer. And then we can use rectangles to approximate it. When we just use 2 rectangles, then this is the estimation. It's way off. The estimation is 5.06 when the real answer is negative 6.75. But now instead of 2 rectangles, let's really up it and say let's use 10 rectangles. So now with 10 rectangles, we get a much better approximation. Negative 5.1975 is the approximation, when in fact the real answer is negative 6.75. We can visually see that it's a much better approximation. But why not take that up a notch? We said 40 in that table, so if we have 40 rectangles, it looks like that. So a much better approximation. And then if we go up even higher, let's use 100 rectangles. It gets even better, right? A much better approximation. So we can just keep playing this game and increasing the number of rectangles until we get a pretty good approximation, as close to the real thing as we want to. Okay, properties of the definite integral. As we did in derivatives, we want to start with the limit definition, and then very quickly want to move on to establishing patterns and properties that we can use so that we can avoid the limit definition if we can, right? Because that thing is a beast to work with. Okay, so we want to start developing properties of definite integrals. So, properties of definite integrals. When we define the definite integral, the integral from a to b of f of x dx, we implicitly assumed that a is less than b. But the definition of a limit of a Riemann sum makes sense even if a is greater than b. Notice that if we reverse a and b, then delta x changes from b minus a to a minus b over n. Therefore, the integral from a to b of f of x dx equals to negative 1 times the integral from a to b of f of x dx. Okay, so we can go forwards and backwards like this. Notice that the only thing that has occurred, the only thing that's different from these two is the limits of integration from b to a, and then from a to b, and then there's this extra minus 1 that takes into effect there. So, for example, what this is saying is that, zoom out a little bit. When we set up an integral, when we talk about the area, we've, assuming that a is less than b up to now, and that's usually the case. So if we have the integral from, say, 3 to 5, this is where a equals to 3 and b equals to 5 of some function f of x dx. That's sort of what we've been working with. On the other hand, if they give you an integral, where it's defined the other way around, where they put the largest number down here and then the smallest number there, that seems a little bit weird, dx. So here we have from a to b, so this is from 3 to 5, and we want to find that area there. So remember that the way we define delta x is equal to b minus a all over n. So in this little scenario, it would be 5 minus 3 over n, which gives you 2 over n. But if it's given to you this way, then we're starting at 5, but leading to 3. That's weird. So even though it's written this way, we can still think of it on the number line in the same direction, from 3 to positive 5. That doesn't make sense to have them backwards. So we can still be talking about the same area. But the thing that does change, though, is that when we calculate our delta x is then equal to 3 minus 5 over n, which gives you a negative 2 over n. Right? So there's this extra factor of minus 1 that comes from the fact that these guys were switched around. Okay, so when I calculate this, remember they're rectangles, assuming f of x is positive, just to not add an extra layer of multiples of negatives and stuff, let's just assume in both cases f of x is a positive answer, just for the purposes of this. So f of x is positive, right? So when I do my rectangles, it doesn't, independent of how you define your domain, you're talking about rectangles that go above it. Either way, I'm going to have rectangles that go from here to here and so on and so forth. Either way, you have rectangles, right? And the base of these rectangles is just going to end up being a negative. So you're just going to get negative answers for all of them. And so that's what this is saying. If we have an integral and you want to switch the limits of integration because they make more sense, you want to put the low to the top, then all you have to do is introduce an extra factor of negative 1. So the integral from, say, starting, right, the lowest number is 13, and then up to 2, you're like, wait, that's backwards. How can you start at 13 and end at 2? It's like you're going in reverse of some function f of x dx. Well, all you have to do is multiply this by negative 1, and then you can flip it, starting at 2, going to 13 of f of x dx. Now keep in mind that this portion of it here might still be negative on its own, right? This thing itself can be positive or negative. So it might be that this is negative times a -1, and then the whole final answer might be positive. So keep in mind that that's a possibility. But it gives us a way of flipping these two around. Okay, so hopefully that made sense. And now this is one of those properties we get to use. Okay, the next property we want to point out is that if a equals to b, then delta x equals to 0. So we're going to have rectangles that have a base of 0. 0 times the height is still going to be 0. So the whole integral becomes 0. Okay, so the integral from a to b of f of x dx equals to 0 in the case where a equals to b. So maybe it would look better if we point out that this is like the integral from a to a of f of x dx equals to 0. And this is in the case where b, this is because b equals to a or a equals to b. Right? Well, if they equal each other, you can also just say the integral from b to b of f of x dx equals to 0. Either way, the point is that if these are the same, then you're not integrating anything. If we have a function like this, y and x, and I say, okay, here's my function, find the area underneath the function f of x, and I want the area to be below the f of x function, above the x-axis, and then trapped between the vertical lines of a, right, starting at a. Normally, we let b be over here, and then we would have our area be this area trapped in the middle. Right, we do rectangles in there and find that area. But in the case where a equals to b, this is gonna get scooted all the way over here to be equal to a, and then we would, we wouldn't have any area, right? We would have a string of width 0. Okay, so here's another property that we get to use. Okay, so here are a nice little table of some of the useful properties, some basic properties for integrals. The integral from a to b on the function c of dx equals to c times b minus a, right? We'll see why this is in a second, where c is any constant. Property 2, the integral of a sum of two functions dx is equal to the sum of the two integrals. Right, so similar to the properties from Riemann sums, we can break it up into two separate integrals. The integral of a sum is equal to the sum of integrals. And then if we have some constant times our function dx, the integral of c f of x dx, we can also pull out the c, similar to the Riemann sums. So the integral from a to b of c f of x dx equals to c times the integral from a to b of f of x dx, where c is any constant. And then this one, similar to that one, the integral of a difference of functions is equal to the difference of the integrals, so you can find them separately. Okay, we will not formally prove these, but let's take a closer look at them. For the first one, we're integrating a constant c. Right? Notice that it's not a function involving x, it's a constant c. So here's a nice little visual representation of that. So for property 1, we're integrating a constant function f of x equals to c. Remember, that's the same as saying it's an equation of the form y equals 2c. So it's just some constant, just arbitrarily, just to picture it, we're going to let c equal to some positive number value here. And so we want the integral, when we ask for the integral from a to b of the function c dx, we want from a to b of the function y equals to c, so the area below the function, above the x-axis, and trapped between the vertical lines x equals to a and x equals to b. So it's this area exactly here, right? So sometimes when the function is not a constant, we've been used to seeing curvy things here. But here we have a straight line. So because we have a straight line, it turns into a nice little rectangle where we just have the length and the width. Think of this as the length and think of this as the width, W, length times width. Okay, so the width is going to be exactly equal to C, and the length is going to be B minus A, right? So that's why this is the formula that we get when we have the integral of a constant. Okay, so for example, if we were asked to integrate from 3 to 7, the constant 2 dx, well then picture-wise, then this would be the number 2 would go here. This would be the line y equals to 2. And then the a would be a 3, and the b would be a 7. So pictorially, we can describe this to be something that looks like this. It's going to be a rectangle. And we want that area right in there. And then this has a height of 2. And this starts at 3 and goes out to 7. So we can see that the area is just going to be the area of a rectangle. It's going to turn into something really easy to calculate. So in this direction, it'll be 7 minus 3, which is equal to 4. And in this direction, this will be equal to 2. So I can say that the integral from 3 to 7 of the constant 2 dx is equal to 2 times 7 minus 3, which is equal to 2 times 4, which is equal to 8. This area equals 8. Okay. Now the second property, which states that if we have the integral of a sum of functions, it's equal to the sum of the two different integrals. This is a very important property that lets us separate one integral involving a summation and separate it into two separate integrals. The goal is then, of course, to hopefully simplify things. So maybe this summation of functions is really ugly, but then when you chop it up into little pieces, then each one of them is a little easier to work with, right? That's our goal. So again, this isn't a proof, but it's a nice picture of why it would be true. So the way you're supposed to interpret this is to think about this function right here, the bottom part. Let me highlight it. So this portion here is representing just the f function. Okay, so this highlighted yellow just represents the f function. And now independent of that, we have the g function. Now the g function goes from this line here. Let me highlight it in red. This value right there goes from there all the way down to the x-axis. So it's not just the part in between. The g function is all of it, all the way down to the x-axis. So on one individual rectangle, if you think about the ith rectangle over here, let's say that this one represents the ith rectangle. Well, this part right here represents the height of the ith rectangle, right up to there. But then going all the way up to, from here all the way up to there, would represent the ith rectangle for the g function up to there. So this and that would represent the height of the rectangle for the g function. And now if we add them together, okay, so just take this one, it's already there, it's the tallest one, and then add to it the f function one. So if we just take the height from here to here, this height, and we come up here and we add it there, then let me highlight it in yellow, and it's getting kind of messy. Then this right here, this by itself, this right here would be the f function value. The height of the f function evaluated at x sub I would just be this part from there to there. And then from here all the way down to the bottom, from there all the way down to the bottom, this is the value of g evaluated at x sub I. So together, all the way up to here represents the whole thing. So the value of f from there all the way out to there represents exactly what we were expecting, f of x sub I plus g of x sub I. Good. Okay, so if you're asked to figure out the area underneath this top curve up here, right, if you're focusing your attention just on this curvature up here in orange, the area underneath, you could say, well, let me find the area below the the red one here that represents just the g. Let's figure out the area below here highlighted in yellow and then add them together, and that should give us the area of the entire thing. Okay, so kind of a geometric explanation of it. Also, we can just go back to our Riemann sum explanation. So we know that this, by definition, is equal to this. The limit as n goes to infinity of the Riemann sum as I goes from 1 to n of the f of x sub I plus the g of x sub I times delta x. And using the properties of Riemann sums, we know that if we have a Riemann sum of a sum, we can separate it this way and do the sum of two different Riemann sums. We have the same property for limits, and now this one represents this, and this one represents that. So a more formal explanation of why this is true. And when we want to think about the negatives, well, it's the exact same thing that can happen, right? So for the same rules, the same reasons, we can do the exact same thing with a subtraction here instead, and then that would be a subtraction, that would be a subtraction, that would be a subtraction, and then that would be a subtraction. So we should have plus or minus for all of these. Okay, in the previous video, in section 5.1, we worked out the following. We figured out R sub n for the case where we had a function, say f of x was equal to the function x squared plus 1, and we wanted to find the area below this function, right? So we had it like this. Here is my function. It kind of went this way, like that. And we wanted to find the area between 0 and 4. And so this kind of comes down like that. And so we wanted to find the area trapped into here. And so we very, very painfully figured out that that area there is equal to the limit as n goes to infinity of the sum as I goes from 0 to n. Oops, sorry. Not 0 to n, from 1 to n. As I goes from 1 to n on the function f of x sub I delta x. Okay, so after a whole lot of work, we figured out that this is equal to 76 over 3. Right, go watch that video if you don't know, if you don't remember that. And so now in this section, now in 5.2, we discovered that this is exactly equal to the notation, the integral from 0 to 4 of the function f of x dx, where our function is equal to this. So I'll say that this is the integral from 0 to 4 on the function x squared plus 1 dx. And so that must be equal to exactly this. So it equals to 76 over 3. Good. So because we already discovered that this was true from yesterday, using today's definitions, we can establish that this must also be true, that the limit of this function, x squared plus 1, from 0 to 4 must be equal to 76 over 3. Okay, so using that information and properties of integrals, let's find the integral from 0 to 4 of just x squared dx. Let's find that. Okay, so it seems like, okay, we'll just subtract 1 from both sides, but it's not quite that. All right, so let's begin by stating this statement over here. So question mark. So then the integral from 0 to 4 on x squared plus 1 dx. Our properties tell us that this must be equivalent to the integral from 0 to 4 of x squared dx plus the integral from 0 to 4 on 1 dx. Right? One of our properties said that if we have the integral of a summation of two functions, we can think of x squared as one function and just the number 1 as another function, then we can separate it as two separate integrals. And then we have that this is 0 to 4 x squared dx plus, and now this is the integral of a constant. And so one of our properties said that this must be equal to the 1, from here, the 1, times 4 minus 0, which is just going to be 4. So we get that this integral, the integral from 0 to 4 on x squared plus 4, and well, we established that that whole thing equals to 76 over 3. So if we just subtract minus 4 from both sides, minus 4, we'll get the requested integral. The integral from 0 to 4 on x squared is equal to 76 divided by 3 minus 4. Common denominator is going to be that 3, so let's put a little 1 there, a 3 there, and a 3 there. So that'll be a 12 divided by 3. And so the integral from 0 to 4 on x squared is going to be equal to 64 divided by 3. Okay, so let's try another one. Or let's add to it. So now that we have that, okay, so now let's use all that information to figure out this integral. Let's say we were given the integral from 4 to 0 on 5 minus x squared dx. Okay, so first of all, we're used to working with the smallest. We start there and end there. So this is the small to the large. And we can see that they're backwards, right? Usually we'd like to see it as 0 to 4. So our first property says that we could just flip it around from 0 to 4, the way we like to see it. The only thing is we have to introduce an extra factor of -1. Okay, so then this would be 5 minus x squared dx. Okay, next, let's figure out what this is. We need to multiply, we need to separate this, so this would be -1 times, I'll just put a giant bracket here. This is going to be the integral from 0 to 4 of 5 dx minus the integral from 0 to 4 on x squared dx. Again, one of our properties says that if we have a subtraction, we can separate it, right? The integral of a subtraction is equal to the subtraction of integrals. The integral of a difference is equal to the difference of integrals. Good. Now this one is just the integral of a constant, and again, we have a nice property that helps us deal with that. This is just going to be 5 times, and then 4 minus 0, minus, and then this one we just figured out. So I'm not really using a known property yet. Eventually we'll get into how to deal with these properties. But for now, I'm just relying on the example I just finished, which indicated that this was equal to 64 divided by 3. 64 divided by 3, reference 2 minutes ago. We figured out what that was. Pay attention to the limits, right? It was the exact same limits. From 0 to 4 on x squared dx is 64 divided by 3. This looks so weird. This 64 divided by 3. Okay, so now we just calculate what this is. Oh, so don't forget that this is for the entire thing. Almost left it there. So this is like this, which then gives me -1 times, and this is going to be +4 times 5 makes it 20, minus 64 thirds. Common denominator is that 3, so let's put a 1 there and a 3 over a 3. Then lead me to say that that integral from 4 to 0 on 5 minus x squared dx is really going to be equal to -1 times, and then this is 60 over 3 minus 64 over 3, which makes it -4 thirds, which is -1 times -4 thirds. And so now the whole thing becomes +4 thirds. Right? So the integral from 4 to 0 on 5 minus x squared dx becomes +4 thirds. Okay, so now the next property tells us how to combine integrals with the same function over adjacent intervals. So if we have the integral from a to c of f of x dx plus the integral from c to b of f of x dx, then that's just equal to the integral from a to b of f of x dx. Again, where the common link here is that this is integrating from a to c, and this one's integrating from c to b. Okay, so pictorially, it would look like this. So we have some function f of x, and the first integral is integrating from a to c, and the second integral is integrating from c to b. And so we can write them down here. So this portion from here to here, this is the integral from a to c of f of x dx. And this integral over here, this area over here, would be the integral from c to b of f of x dx. And if we're adding them together, well, you can see that, well, that's just going to be the same as integrating from starting from a all the way out to b on the function f of x. So the whole thing is just equivalent to the integral from a all the way out to b on f of x dx, right? And that's when that property comes in. So it's not easy to prove in general, but for the case where f of x is strictly positive, and so c is strictly between a and b, this property can be seen from the geometric interpretation, right? So this isn't a proof. This is just common sense interpretation of it. And we're sticking to some nice assumptions that make things nice. So f of x is positive above the x-axis, so we're not worrying about going below or above the x-axis. We're not looking at cases where c is actually equal to a or c actually equals to b, or if c might be not inside, not between a and b. So we're not considering any of those cases that might make things a little bit more confusing, but a very straightforward application, and it can be seen from common sense that if they're adjacent like this, then we can simplify it. Okay, but we're not going to worry about the proof of this at this point. Here's some other properties. So the comparison properties of integrals. So for properties 1 through 5 are true when a is less than b, a equals to b, or when a is greater than b. The following properties in which we compare the sizes of functions and sizes of integrals are true only if a is less than or equal to b. So now we really do care to make sure that a is the smallest number or equal to b, or b is greater than or equal to a. Okay, so property 6, if f of x is greater than or equal to 0, and x is between a and b inclusive, then the integral from a to b of f of x dx must be greater than or equal to 0. Right, this has been our common interpretation of the area underneath a function. So in cases where the function is positive, then the integral will give us a positive answer as well, or 0. Property 7, if f of x is greater than or equal to g of x, for x being between a and b inclusive, then the integral from a to b of f of x dx will be greater than or equal to than the integral from a to b of g of x dx. Again, I think that kind of intuitively makes sense, but we're not proving it. These are great proofs for some other class, but we're not doing that here. And finally, if lowercase m is less than or equal to f of x less than or equal to capital M, right? So f of x is trapped between some lower bound, lowercase m, and some upper bound, capital M, for x between a and b inclusive, then our integral from a to b of f of x dx will also be trapped between these two values. It will be an upper bound, which is capital M times b minus a, and this product, which is lowercase m times b minus a. So this picture helps us visualize that, and it's a very intuitively true statement as well. So if we have some function like this, and so here is capital M and here's lowercase m. So let's say that this point right here, see the tallest value in the function is still smaller than capital M. So capital M represents an upper bound. Now it could be equal to it, or it could be that M is just way up here. It just represents some maximum height that F never reaches. Likewise, lowercase m represents a lower bound. The actual function is never below it. Good. Okay, so now the area, the integral, right? The integral from a to b of f of x dx, well, that's going to be this entire area here, all the way down to here, all of this. Everything that I'm identifying, all of that represents the area I'm interested in. Now, we sometimes don't want the actual answer. It might be too difficult to find the actual answer. But if we can at least establish an interval, we might be happy with that. And so notice that everything I've highlighted here must definitely be larger than just this dark blue rectangle in the denominator. So if we just focus on this rectangle down here, the area underneath the function, the thing we're interested in, is definitely greater than or equal to this yellow highlighted rectangle, which has got a height of lowercase m and a width of b minus a. So that's why it's this lower boundary of m times b minus a. And then exactly the same idea comes into the maximum. If capital M represents a value that is greater than any value of our function, then if we think about this ginormous rectangle here that's made up of everything going from there all the way out there, this ginormous rectangle, it has the same base of b minus a, the same base, and it's got a height of m. And that's how we establish the upper bound, capital M times b minus a. Good. So that's what that one is stating. And like I said, this one is often useful in cases where the actual integral might be very difficult or maybe even impossible to figure out. But we might be okay if we settled on some interval, if we at least established that the answer is greater than something, smaller than something. These two outer ones, the lower boundary, the upper boundary, are potentially, hopefully, easier to solve, to find. So that might be good enough in those cases. Okay, so this should be more than enough to do your homework. Please work on it and let me know if you have any questions.